This is the 18th video in a series devoted to introductory proofwriting. In the previous couple videos, we looked at relations on sets. And for a brief minute, we looked at a relation between two sets. And today we want to look at functions, which is really a very special type of relation between two sets. So let's look at our proper definition. So we'll suppose that A and B are sets, and then a function f from A to B, which we'll denote with the following notation. So read this as f is a function from A to B, is a relation. So that means it's a subset of A cross B, such that for every A in A, there is exactly one B in B. So that should be a lowercase b, such that the ordered pair A comma B is an element of F. Remember that F is really just a subset of A cross B, so at its heart. And so generally we'll write F of A equals B. And so that's like proper, maybe very common function notation that you know from pre-calculus or calculus class. But another notation we could use is this A gets sent to B, or A is mapped to B. So notice it's this arrow with this little vertical line here. And then if we're working with more than one function, we might put a little f over this to say that that mapping is done via f. Now there are things associated to functions like the domain, and so the set A is known as the domain of f. Then B, which is the target, is called the codomain of f. Notice that's not the range of f. The range is only the points in B that get landed on. So in other words, it's everything of the form f of A as A runs through all capital A. So like I said, that's called the range of f, or sometimes the image of f. Okay, so now let's look at a very basic example and then non-example as well. So let's look at this function f. So it takes A to 1, B to 3, C to 4, and D to 3. I guess I should say that A is the set A, B, C, D, and B is the set 1, 2, 3, 4, 5. So we could maybe draw this in a picture like this. So we could have a bubble over here that's A, so it contains A, B, C, D. Then we could have a bubble over here that is B, so that's 1, 2, 3, 4, 5. And then we'll notate this as arrows. So A gets mapped to 1, so there's our arrow. B gets mapped to 3. C gets mapped to 4. And then D also gets mapped to 3. So we have something like this. You know, we could also write it as f of A equals 1, or as A gets sent to 1. We could also write f of B equals 3, or B gets sent to 3, and so on and so forth. So those are just different ways of writing the same kind of thing over and over. Let's compare that with this R over here, which is a relation but not a function. Let's draw a picture of that. So we'll have our set A, which is made up of little a, little b, little c, little d, and then our set B, which is the numbers 1, 2, 3, 4, 5. Now notice this tells us to take A to 1. Okay, that's cool. B to 2, so everything is still okay. But it also tells us to take A to 3. And that's where we have our problem. Notice over here that every A in A, there is exactly one B in B such that A comma B is an F. But this A is connected to two elements from B, 1 and 3. So that's how you can see it in the set. In the picture, we can see that as having two tails of arrows based at A. Okay, so now let's continue on. So C gets mapped to 4 under this relation, but notice D is not sent anywhere. And that breaks a rule as well. So notice for every A in A, there is exactly 1. Well, D has 0 elements that is mapped to, so that is not exactly 1. So there are a couple of different reasons why this relation is not a function. So before moving away from this example, I'd like to do one more visualization. So I'd like to take one more visualization of our function, and I'll maybe leave the visualization of the relation as maybe a warm-up problem, or maybe an exercise for you to do on your own. So here's what I have. I have the set A cross B, so down here on a horizontal axis, if you will. It's not exactly an axis. We have our set A, and on the vertical, again, axis, we have the set B. Now what I'd like to do is graph this function. So this is like an interesting discrete function on two finite sets, so it's not like a graph like you might see in a calculus class. So notice it will contain this A comma 1 element, but then after that we have to sneak up here and then we contain this B comma 3 element. So that would be the next thing that it contains. Then let's see, then we sneak up here and it contains this C comma 4, and then we sneak down here and it contains this D comma 3. So in the end, the graph would be this like blob that's going through A cross B containing all of these ordered pairs. But notice this blob passes like some version of the vertical line test, which is the test that you might have used in calculus or pre-calculus to determine if something was a function. Now, like I said, I'll leave it to you as an exercise to graph this relation and see that it's not quite as nice, or you can see the visualization of the fact that this is not a function. Okay, so let's move on. For our next example, let's consider the function f. Its domain is the integers and its codomain is the natural numbers. And we'll define it via this rule here. So this is like a standard way of defining a function. So we have when f acts on n, it gives us the absolute value of n plus 1. Or we could also similarly or equivalently define it by this arrow rule. So we have n is mapped to the absolute value of n plus 1. Now let's look at a couple of examples of evaluations, although this is quite simple. Notice f of 3 will turn into the absolute value of 3 plus 1, which is 4. F of negative 2 will turn into the absolute value of negative 2 plus 1, which is 3, and so on and so forth. So in fact, we could graph this if we wanted to, and I would say that'd probably be something nice to do. So notice the number 0, so f of 0 will give us 1, so that would be this point right here. F of 1 will give us 2, so that would be this point that's about right here. F of negative 1 will give us 2 as well. F of 2 will give us 3. F of negative 2 will give us positive 3, just like we saw before. And as you can see, we will essentially get this shape, which is a bunch of dots in a V. And those dots all lie on this like lattice of the integers and the natural numbers. So something like this. So you can imagine this as being the lattice of the integers and the natural numbers. Okay, let's do another one. So for our next function, let's look at phi, which goes from z squared. In other words, z cross z to z. So it has an input of 2 integers and an output of 1 integer. And it's defined by the following rule. Phi evaluated at mn is 14m minus 8n. Now I think maybe something good to do with this function is to determine its range. So let's get a good guess for its range by evaluating this at some points just to see what we get. So let's notice that phi evaluated at 0, 1 will be equal to negative 8, just based off of that rule. Phi evaluated at 1, 0 will be equal to 14 based off of that rule. Notice that phi evaluated at 1, 1 is 14 minus 8, that's equal to 6. What about phi evaluated at 1, 2? So that'll be 14 minus 16, that is negative 2. Oh, but what about this? What about phi evaluated at negative 1, negative 2? So that'll be negative 14 plus 16, which is 2. Okay, well, what do we notice about all of these numbers? Well, in fact, they're all even. And this is the smallest positive even number, and this is the smallest negative even number. So it seems like we're just getting all of the even integers. And that'll be what our claim is. And we will prove this claim. So here's our claim that the range of phi, let's maybe write it like that, the range of phi is equal to all even integers. So we could write this as 2 times k such that k runs through all integers. But let's recall using some notation similar to what we had in a previous video. That could be 2z. That says we're scaling every integer by 2. Okay, so let's see how this proof goes. Our goal is to show that two sets are the same, which means we need to do this with double inclusion. So let's do that. So we'll start with the inclusion going this way. So let's suppose that we have a number L, which is in the range of phi. But what does that mean? That means that L equals phi of mn, which equals, let's see, 14m minus 8n for some m and n, which are integers. That's what it takes to be in the range. But now let's notice this. Note that we have L equals, well, 14m minus 8n, but we can factor a 2 out of that, leaving us with 7m minus 4n. But that's very clearly in this set of even integers because it's multiplied by 2 and then 7m minus 4n is an integer. So let's just write this is in 2z, since that's some nice short notation. Okay. So that means we have proven the right inclusion, or the inclusion in that direction. So let's move on to the reverse inclusion. So let's suppose that we have a number, what should we use this time? Let's maybe use 2a, which is in 2z. Well, remember 2z, that's all even integers, so that means it's of the form 2 times a. And then let's observe the following calculation, which can be motivated by this up here. This phi of -1, -2 is 2. So if we have phi of -a, -2a is equal to, let's see, this will be 14 times -a minus 8 times -2a, but after fairly simple calculation, we'll see that that is equal to 2a. But this equation shows us that 2a is in the range of phi, because we wrote 2a as an output of phi. That's exactly what it means to be in the range. I left out an e there. But that's exactly what we need to finish off this reverse inclusion. So the forward inclusion and the reverse inclusion finish the proof that the range of this function, or the image of this function, is indeed all even integers. Okay, so now let's move on to some special types of functions. Now we want to look at some special classes of functions. So let's see the definition. Given a function f from a to b, we say that f is injective, or in other words, 1-to-1, if for all x and y in a, we have f of x equals f of y implies x equals y. Then we call it surjective, or onto, if for every b in, that should be b in b, we have an a in a such that f of a equals b. So this means everything is landed on. And then we say it's bijective if it's both injective and surjective. So let's look at some pictures of functions that are injective, not injective, and surjective and not surjective. Okay, so first for an injective function. Let's say we have the following action like this. So these 3 dots, notice they're all mapped to 3 different places in the codomain. That's exactly what we need for this to be injective. So everything from the domain is mapped to a new thing in the codomain. Let's compare that to something that is not injective. So let's say we have some action like this. So notice this second and third dot are both mapped to this second dot. So they're mapped to the same thing. That makes this thing not injective. Notice if this were x and this were y, here we have f of x equals f of y, but x is not equal to y. Okay, now let's go over and explore a surjective and a not surjective function. So a surjective function means everything in the codomain is landed on, and this would be an example. Notice every dot over here is mapped onto. Then something that's not surjective would be something like this. So notice that this dot over here is missed. So you can think about something that's surjective, doesn't miss anything in the codomain. Okay, so next I'd like to give some outlines for proving that functions are injective and surjective, and then do some examples. So now I'd like to look at some proof outlines for proving injectivity and surjectivity of a function f from a to b. So in order to prove that it's injective, you'll start by supposing you have x and y in A such that f of x equals f of y, and then you will decode that or unpack that using the definition of f and do some calculations here. That's what this purple box is, to finally end with x equals y. And so that'll complete this proof. And then showing that f is surjective is a little bit trickier. So in your scratch work, you will solve f of a equals b for a. And what you'll get is a is written in terms of b. Then you're ready to write down your final proof. So we'll suppose that little b is in b and consider a equals, well, this crazy thing that you found after solving this. And then next up, you say something like, now observe that f of a equals b, but this is going to involve essentially the reverse calculation of this over here. Okay, so I think it's best to look at some examples of this. So let's first consider the function f that goes from the real numbers minus 0 to the real numbers defined by f of x equals 2 over x minus 1. And we'll show that that is injective but not surjective. So let's start by showing that it's injective, and then we'll show that it's not surjective by finding someone who is missed. And then we'll redefine the codomain to make it surjective. Okay, so injective. So let's suppose that x and y are in the set of real numbers minus 0, where f of x equals f of y. And now let's unpack that and see that that means that 2 over x minus 1 equals 2 over y minus 1. But now essentially we just solve for y or solve for x. It's the same kind of thing. So we can add 1 to both sides to get 2 over x equals 2 over y. Then we can invert this and we'll see that x over 2 equals y over 2, which means that x equals y. But that's exactly where we needed to end up to show that this was injective. So now let's show that it is not surjective. And the way to do this is to think about the horizontal asymptote of this function. Notice the horizontal asymptote will be -1. If we let x approach infinity, this thing will disappear and we'll have -1, and that's going to be the thing that is missed. So here's our claim, and that is there is no x from the real numbers minus 0 such that f of x equals -1. And how can we see that? And we can see that because, so let's do a little proof of that. So let's set f of x equal to -1 and show that we get no solution. Notice this is the same thing as 2 over x minus 1 equals -1, which is the same as 2 over x equals 0. But let's notice that 2 over x equals 0 has no solution. But that's exactly what we needed. Okay, so now let's maybe fix this and change this codomain from the real numbers to the real numbers minus -1, and now we'll show that it is surjective. So let's put an and here and we'll show that it is surjective. Okay, so the first step to showing it's surjective is to do this scratch work. Remember that scratch work is where we solve. So let's solve the equation f of a equals b for a. So let's see, that means we have 2 over a minus 1 equals b. That's the same thing as saying 2 over a equals b plus 1. But then that's the same thing as saying that a is 2 over b plus 1. Now we can see why b is not allowed to be 1. Also, that gives us a 0 in the denominator of this expression. So that would be our a. Now we're ready to show that this is surjective under these new conditions. So let's suppose that b is from the set r minus -1, and then let's set a equal to 2 over b plus 1, based off of that side calculation. Okay, now from here, let's do our final calculation. So we have f of a, so that's going to be equal to, let's see, 2 over a, but that's going to be 2 over b plus 1 minus 1. Great. But now you can simplify this. Maybe I won't go through all the details, but if you simplify all this, you'll see that you get b, but that's exactly what you need to get for surjectivity. Okay, let's do another. For our next example, we're going to consider the function which I'll call g. It goes from z2 to z2. So in other words, from 2 copies of the integers to 2 copies of the integers, z cross z. And it's defined by g evaluated at m comma n is 2m plus 3n comma m plus 2n. Now our goal is to show that this is bijective. So let's start by showing that it's injective. So let's suppose that we have m comma n and maybe what I'll call m prime comma n prime in z2 such that g of m comma n equals g of m prime comma n prime. And what we want is for these two ordered pairs to be equal, which means both of their entries are equal to each other. In other words, m is m prime and n is n prime. Okay, so let's notice that this equation right here turns into the equation involving the outputs. So we have 2m plus 3n comma m plus 2n is equal to 2m prime plus 3n prime, and then m prime plus 2n prime. Okay, but what does it mean for ordered pairs to be equal? Well, ordered pairs are equal if and only if both entries are equal. So that means we need this entry here to be equal to this entry here. We also need this second entry to be equal to this second entry. So let's bring that down. We have 2m plus 3n must be equal to 2m prime plus 3n prime. And furthermore, m plus 2n must be equal to m prime plus 2n prime. Okay, great. But now, where would we like to go from here? Well, something that I would like to do is perhaps add these two equations with some scaling. So I think maybe our best bet is to take the second equation, multiply it by -2, and then add these two equations. Why? Because that'll cancel the m's here and the m primes here. So let's see, we'll have 2m minus 2m, that's 0. We have 3n minus 4n, so that's -n. Then the m primes cancel similarly, and then we'll have -n prime over here. But if -n equals -n prime, that means n equals n prime. Okay, great. But from here, it's a short trip to see that m and m prime are the same as well. We can perhaps take this and plug it into this first equation and do a very little bit of simplification to see that m is equal to m prime. Okay, but if m is equal to m prime and n is equal to n prime, then that means that m comma n is equal to m prime comma n prime, which is exactly what we needed to finish this proof of injectivity. Now let's show that it's surjective. Now we'll show that it's surjective. Recall that involves a little bit of a scratch calculation. So what we'd like to do is solve gm comma n equals maybe a comma b for the ordered pair m comma n. So notice that's the same thing as 2m plus 3n equals a, and then m plus 2n equals b. Just by using the definition of G, and then again the fact that ordered pairs are equal if and only if their entries are equal. Okay, but now we'll do essentially the same thing that we did before. So let's take this, multiply by -2 and add, or maybe multiply by 2 and subtract. It's the same kind of thing. So that's going to give us 2m minus 2m, which cancels, 3n minus 4n, so that's minus n, equals a minus 2b. But notice that means that n is equal to minus a plus 2b. Okay, good. And now let's swing that back into one of the earlier equations and see what that leaves us with. Perhaps we'll swing that back into this first equation. So that leaves us with 2m plus 3 times negative a plus 2b equals a. Okay, so that gives us 2m minus 3a plus 6b equals a. So we get 2m equals, let's see, moving that around, we'll have 4a and then minus 6b, which means m equals 2a minus 3b. So there we have it. We have values for m and n that will make this work. Okay, so now we're ready to write this up. So let's suppose that a comma b is in z cross z, in other words, z squared, and set m comma n equal to this thing that we calculated over here. So 2a minus 3b, comma, minus a plus 2b. And then observe that g evaluated at mn, well, that's going to be the same thing as g evaluated at this, so 2a minus 3b, comma, minus a plus 2b. But by the rule up here, we know that will be equal to 2 times 2a minus 3b plus 3 times negative a plus 2b. That's the first entry. And then the second entry is 2a minus 3b and then plus 2 times negative a plus 2b. So that's the second entry. So just to reiterate what's going on here, because it's kind of messy, this is 2m plus 3n, and then here we have m plus 2n as needed. But now you can simplify this just doing standard calculation, and you'll see that you get ab in the end, which is exactly what we need. We found this, what's called a pre-image for the element ab. Okay, let's maybe do one more quick one and then I'll leave you with some warm-ups. For our last function, we'll call it h, and it goes from z cross z to q, and it's defined by h of mn equals m over the absolute value of n plus 1. And our goal is to show that this thing is surjective but not injective. Okay, let's show that it's surjective. These are actually pretty quick, and we don't actually need to do a bunch of side calculation here because we can kind of guess and check our way to it. So let's suppose that we have a over b in q. So we know that every element of the rational numbers can be written as a over b, where a and b are integers, but b is not equal to 0. And now let's observe that h evaluated at a comma, let's see, b minus 1 will give us a over the absolute value of b minus 1 plus 1. But that's going to end up giving us a over b. But notice this doesn't quite work if b is negative, so we might as well choose b to be bigger than or equal to 1. And you might say, well, how do we know we can do that? Well, every rational number can be written with a natural number denominator, so that's totally fine. And now everything works out perfectly. Okay, so now let's show that this thing is not injective, and we can do this by counterexample. So let's first note that h of, let's see, 2 comma 0 is equal to 2 over 0 plus 1, which is the number 2. But I think we can maybe hack this together. Notice that h of 4 comma 1 is equal to 4 over 1 plus 1, which is also equal to the number 2. So we have two elements that are not the same. 2 comma 0 is not equal to 4 comma 1, but they evaluate to the same number via the function. So this means it is not injective. Okay, let's leave you with some warm-ups. So here are 3 nice problems to practice what we've seen today. So let's consider the function f from z to z squared, or z cross z. Let's define it by f of n equals n minus 3 comma 3n plus 2. Notice the output needs to be in z cross z, so it has two components. Then next, with proof, decide if f is injective and or surjective. So for our next one, let's consider the function g. It goes from r minus 3 to r minus 2, and it's defined by g of x equals 2x plus 1 over x plus 3. Let's show that is indeed bijective. And finally, let's define a function h from z cross z, in other words, z squared to z, defined by h of mn equals 3m plus 5n. And you can show that that is surjective but not injective. And that's a good place to stop.